believe that one of the conditions for all of this to work is that the nth derivative of u, that nth component of the gradient, is not equal to 0. Right, and the idea there is that we don't want perpendicular vectors. We want tangent vectors to this surface in order to derive these equations. So this is kind of general. I'm hoping it's making some sense with what we're doing with it. I'm not sure how much of the details I want to cover because most of them are sort of complicated. One example that I can give of an equinal equation to try and understand some of this language, I'll do it here. They write it this way. They write it the differential form of phi is equal to 1, right? If we sort of decompose this and think of the association between this and the gradient that we've talked about, well, this equation is just d phi dx squared, and then I, summing over I. So it's just this equal to 1. So it's similar to what I have written, except normally, again, when we talk about method of characteristics, we talk about the quasi-linear case, where this A is a function of u as well, or the C is a function of u. In this case, the nonlinearities that we're talking about can also be nonlinear in the derivative, and that's kind of the advantage, kind of the power of this approach, as well as talking about all of this on a manifold in a nonlinear space. So this is what they call a simple example of an equinal equation. Let's see. And they say that this surface, right, so they talk about, I don't remember, do you guys have a good grasp of the Poincare lemma that we've talked about? Do you remember what it says? Nope. Okay, so I won't go into this very much, but I'll mention it. What he was talking about saying that we have exact forms and we have closed forms, right? A closed form is one that if we take the exterior derivative of it, it's equal to 0, right? If I have that terminology correct. And then an exact form, or maybe, now I have them confused. The other one, whichever was the correct first one, is where it is a differential of some other function or some other form, right? So we say, if I have this correct, that u is exact if it is the differential of alpha, right? No, u is closed if it's the differential of alpha, right? And then the Poincare lemma is, well, we know one direction. We know immediately that du is equal to 0, right? Because d squared of any form is 0, right? And this can be proven because of the anti-symmetrization of indices. And I think Dr. Overmead spent some time here. And it actually comes from this, and I won't go into the proof, but that's sort of the outline of the proof. This condition that u is an exact form, not u is an exact form, u is a closed form, is exactly the condition we need to describe this surface lambda. Locally, of course. Right, and then it brings in the symplectic form, and the connection between the Hamiltonian system stuff and the stuff that we're doing now with first order PDEs is exactly through this association of the differentials of x with the momenta, right, that we've been talking about for a few days. So again, I'm not going to go into the details, but he talks about the symplectic form that we also have mentioned in this seminar, and then derives a condition that this lambda is the graph of du locally, if and only if, right, the symplectic form of any tangent vectors to lambda is equal to 0. So it allows us to say that, again, kind of complicated terminology, at least in my mind, fairly difficult to present in a seminar. The idea is that we can associate this PDE to some Hamiltonian system, and we can talk about all of the vectors that are tangent to it, right? And the analogy, the point behind all of that is that we can effectively reduce this first order nonlinear PDE in some sense, locally to a Hamiltonian system, which is a system of ordinary differential equations, right? So I don't think I'll go into much of the details of how this is done. I will also mention that it brings in, of course, the geodesics that we've talked about and we spent some time on, at least I hope we did, and uses that to derive some certain special cases. I don't think I'm actually going to present anything else, because I think, personally speaking at least, that if I go any farther into the geometry, you guys will be confused and I will get more confused. So I hope this is kind of like a brief summary of, you know, some motivation for why we care about geometry. At least that's what I'm taking from it. The rest of the book is very geometrical, so I guess more and more we see differential forms, the more and more we see a lot of this stuff, hopefully it makes a little more sense. For me at least, I like relating it to what we have covered in other classes, and what at least makes much more sense to me is this very simple Euclidean linear stuff. Yeah, and there are some special, very particular cases where he can derive, or where the author has derived several nice formulae. If we assume that the metric is Euclidean, then we get these kind of straightforward, from his perspective, formulas for the solutions to these equations. Yeah, I don't think I'm going to mention anything else about this. Did anyone read this section? Okay.
Which section are we on?
15.
Okay.
I do want to mention, I was not able to follow this because my recollection of covariant derivatives is very poor. But there is a trick, and I do not know what this trick reduces to in Euclidean space, so I may have to look into it. But there's a trick of reducing any equation of this form, which is a fully nonlinear, right? Completely nonlinear, non-autonomous, well, that's not true, it is autonomous. Fully nonlinear autonomous first order PDE into an equinal equation, and they call it Jacobi's trick. And I believe the tool he uses is covariant derivatives, which, have we talked about those at all? Okay. Say again?
Mention them.
Okay, so I could write the formulas up for you guys, but I don't think many people would get much out of it. But I think it is useful to know that such a trick exists, so that if we can focus on the study of this system, and we can take all of these results, and then there's this nice trick that allows us to talk about all first order equations in some sense. But yeah, this is at a much higher level, much more theoretical than, say, 336 in terms of, you know, can I even write down a solution? At the end of the day, for a very simple problem, we were, you know, Avermedi and I spent about an hour, and we worked out a solution, but the solution is not very nice. Oh, and one other thing to mention, using these techniques, do you guys remember, can you tell me off the top of your head what the problem with deriving a solution via characteristics can be, especially in the nonlinear and the quasi-linear case? Like what happens, say, in the quasi-linear case very often? For example, if I give you this equation, ut plus ux equals 0, right? And I give you an initial condition, u at x and 0 is equal to x for 0 less than x less than 1 and 0 elsewhere. Well, so the initial condition is like this, right? And you've all seen this in coursework, I imagine, I hope. And what happens immediately to this point? Well, this point travels forward with characteristic speed 1, right? And this is traveling forward with speed 1, and this point is traveling forward with speed?
Whatever that point is.
Right, like half or something, right? So the idea is that this breaks, the solution breaks down. It doesn't work, we have to fit a shock to it, right? And that comes from the fact that when we do characteristics, we're parameterizing things by these lines, these characteristics, and they intersect. This solution breaks down for t, much bigger than 0, and this much bigger could be, in this case, equal to, right? It breaks down immediately in this case. That aspect is true of all of the theory developed in this section, which, again, I apologize for not going into it in detail. I just don't see much of a use, and I don't have enough of a grasp of it. But that brings me to topic 2, which is where do we want to take the rest of this seminar. But this